Hi Margaret, this is a video about chapter 6 stuff. I think it's a little bit old from what you're doing in class, but it might help you give some explanations to some things. As I've mentioned to you before, I think it's a mistake just to try to focus on how do I solve this problem or that problem, but have a more broad understanding of what you're learning. I think this is really an important slide. Let me try to explain why. I am going to write important. The reason is that this explains the idea that when you have a system, you have quantum states when electrons are in atoms. Now, what does this have to do with a guitar? Basically, what this picture shows is that you can pluck a guitar string in this picture 3 different ways and have 3 different patterns of what the string's vibrations look like. You could have this first one where the vibration is just up and down like that, or you could pluck it where you pull up on one side and down on another and then let it go, and the string is vibrating. The thing you're supposed to notice from the left side of this picture is that only certain wavelengths are allowed. And that's the Greek letter lambda, which you should recognize as a wavelength. Let's say that this guitar string is 3 feet wide. What's the wavelength of this middle wave state, let's call it? Well, you would say that the wavelength is 3 feet, because if the whole string is 3 feet, this string pattern goes up, down, and back to the original, and so that's exactly 3 feet. In the bottom one, the wavelength is 2 feet. Why is it 2 feet? Well, if you see the pattern go up and down and back to where you start, that takes 2 feet to do. The string's 3 feet long, but that's an extra half a wave. But the wavelength, the length of one wave, is 2 feet. The top one's a little harder to see because this is only half a wave. The wavelength is actually 6 feet. Again, being half a wave, it would require another 3 feet to be a full wave, so that's why the wavelength is 6 feet, even though the string, it's kind of theoretical, but the string is 3 feet long. The point of this is only certain wavelengths are allowed. There are no patterns that give like 2.5 feet or something like that. You actually have an infinite number of patterns. If the waves get smaller and smaller and smaller, you can get smaller and smaller wavelengths, but you can't get any wavelengths in between those patterns. This slide is a mess, but essentially, here's the part that's important down here. The proposal that all particles have a wavelength is only detected if the particle in question is super tiny. So on the previous slide, we were saying that electrons have wavelength. What does it mean that an electron has a wavelength? Well, it means it does things that waves do. Does things waves do. And if you remember from my previous slide, we talked about some of those things that waves do, and I'll show you in a picture in a second. But the proposal that all particles have a wavelength is only detected if the particle in question is super tiny. The diameter of an atom is around 10 to the minus 10th meters, which is around the lower limit of our ability to detect the particle. What this means is that if you have something like a baseball, there's no way you could detect that wavelength because it's 10 to the minus 34th. Too small to detect any wavelength. This is what I told you waves do. Notice that this is X-rays causing a diffraction pattern, meaning that there's light and dark rings after they hit something. Electrons do the same thing. This is evidence that particles can act like waves. You know light is a wave, right? And so there's an electron acting as a wave. The pattern on the right shows that a stream of electrons can behave just like a stream of photons. Now this gets super theoretical, and I don't know if they talked about it in your class, but there is something called the Heisenberg uncertainty principle. This is an implication of the wave nature of particles, is the uncertainty principle, which states that it's not possible to know both the position and momentum of a moving particle at the same time. The more accurately you know the speed of something, the less accurately you know the position, and vice versa. Here's what we mean by that. Let's say an electron is flying through the air and you want to know how fast it was going. Well, how would you know how fast it's going? Well, one way you could do is shine light on it. You could shine light on something, and then the pattern that it comes off will tell you how fast. But the problem is that even though that shining the light on the electron can give you some information about how fast it's going, it's not going to be exact. And it also is going to be fuzzy exactly where the electron is. So you can't know the position and the speed at the same time arbitrarily. So what is the impact of the uncertainty principle on our knowledge about what's going on inside an atom? It means that even though we cannot know the exact location of an electron, the wave equation allows us to solve for the energy states associated with the electrons. In short, the square of this wave function gives the probability density, a measure of the probability of finding an electron of a particular energy in a particular region of the atom. You've seen this. You've seen three-dimensional pictures of these functions. These are called orbitals. So here's a bunch of pictures. What these are really pictures of wave function probabilities. What this means, let's look at this little guy here. That tiny little sphere is a 1s orbital. What that 1s orbital is represented in these sentences. The solution to the Schrödinger equation yields the probability in 3 dimensions for the likelihood of finding an electron about the nucleus. That means if you have an electron in a 3s orbital, that little dot is where that electron spends its time. These probability functions give rise to the hydrogen-like orbitals that electrons occupy. When we talk about taking an electron, let's say we have an H atom, and you only have one little electron, and you put it up to an excited state. What these pictures are showing you is that electron gets thrown into a different shaped orbital. So look at this 3s orbital. It's much, much bigger than a 1s, and actually there's like a little bead inside where it even has a higher probability of being. Remember again that these are maps of probabilities. You really shouldn't think of them like a peanut shell and something's bouncing around inside. There's different places in the nucleus, let's say like close to the nucleus where there's a high probability, and then there's a lower probability out here, and then there's no probability outside the thing. Here's an inside look of what the 1s orbital looks like. So this is really a 1s orbital. You could draw it as a sphere, and this just basically says the electron, quote, lives in this space. But even that space is even more a little detailed. Take a look at what's going on here. See these pictures? Those dots represent probability. What this means is that the electron loves spending time really close to the nucleus and less and less farther away. So the density of the dots tells you the probability, and you could see that in this picture. Notice how it's really a high value super close to the nucleus, and it's a low value far away. That's the pattern of those dots. An atomic orbital, like I just had on the previous slide, has 3 quantum number labels that convey characteristics of that orbital. The n value, which you already know about, that tells you what energy level it's at, and it also gives you the relative size of the orbital. The L value leads to the shape. You might remember this. If L is 0, that's an S. If L is 1, that's a P. If L is 2, that's a D. If L is 3, that's an F. So that tells you the shape of the orbital. The magnetic quantum number, m sub L we call it, is an integer with values from minus L to plus L. It indicates the orientation of the orbital. So that tells you, let's say if you have a P-shaped orbital, it could either be pointing in one of 3 directions. -1, 0, and +1. So there are 3 different p orbitals that are in shells that have that value. Now there's no p orbitals in an n equals 1 shell because n is too small. But when n is equal to 2, well then the L can either equal a 0 or it could equal a 1. So for the s orbital, there's no choices about what the m sub L could be. So this guy you could think of as like 2, 0, 0. there. The p orbitals, though, you could have a different value of m sub l. It could be, as I said, minus 1, 0, or plus 1. So this guy you could think of as 2, 1, minus 1, 2, 1, 0, 2, 1, plus 1. So each orbital has its own three number labels that represent that. So every orbital has a unique set of 3 of these numbers, every orbital. We're going to say something different in it about electrons. This is a summary of what I was saying before. You see how these numbers at the top, the n equals whatever, that tells you what shell you're in. The first shell, the second shell, the third shell. Inside each shell are different subshells. So in the n equals 3 shell, you could either be a 3s subshell, a 3p subshell, or the 3d subshell. Then the m sub l tells you how many orbitals of each type you have. So notice that there's only one s orbital, regardless of what shell you're in. There's 3 p orbitals, regardless of what shell you're in, and 5 d orbitals, regardless of what shell you're in. You might also notice that as the shell numbers get bigger, things get more complicated. You have a lot more orbitals. Notice that there's a total of 9 orbitals in the n equals 3 shell. This will allow you to know how many electrons can fit in the shell. Things can get really complicated. I don't know if your teacher is telling you about this, but as the n values get bigger, the probability gets more complicated. Notice that the 1s orbital is really simple. It looks like a hard-boiled egg, and the darker spot is in the middle. But the 2s and the 3s get more complicated, where you see dark and light spots. That's because these little things called nodes are there. See where there's 0? The probability equals 0 at a node, N-O-D-E. So there are 0 nodes in the 1s, 1 node in the 2s, see where it touches 0, and then 2 nodes here. So we're looking at the places where the wave function touches the bottom, where it's a 0. That means that the electron can have no chance of being at that location. P orbitals kind of look like dumbbells. This is the way that I usually draw it, although it looks like they're saying they're a little bit fatter than that. But here we have the electron bouncing around, and it has probability that looks like that. 0 chance being in the nucleus, obviously, and then a higher chance of being that far from the nucleus. And then to get really far from the nucleus, it goes back to 0. D orbitals kind of look like 4-leaf clovers. There's actually 5 of them. So let's say in the n equals 3 shell, you have 5 orbitals. That's because the m sub l could be minus 2, minus 1, 0, plus 1, or plus 2 m sub l. For the 3d orbitals, the n is equal to 3 and the l is equal to 2. And the m sub l could equal those 5 numbers. I don't know if your teacher makes you name them. We don't make them, the students name them. One of them looks weird. 4 of them look like 4-leaf clovers, and then this one looks like a p orbital with a donut around it. When you mix them all together, it kind of looks like a crazy balloon animal. F orbitals have these basically 8 lobes. Whoops, my bad. 8 lobes in a F orbital. Remember that the d orbital had 4 lobes. It's like a 4-leaf clover. This is like a whatever. Notice that, remember when we're doing emission spectra before, all you cared about was what the n values were. Like if the n equals 2 goes to n equals 1, or the n equals 3 goes to n equals 1, and then the wavelength corresponds to that. Like the energy of the photon is equal to hc over lambda. This energy is bigger because notice that the distance it goes from the high level to the low level is longer. But the energy of the photon only cares about n, only cares about n, what shell you're in. Notice that for the H atom, all of the orbitals, the 3s, the 3p, and the 3d, have exactly the same energy. We're going to see in a minute that that's not true for a bigger atom. Oh, this little thing, maybe it's a little bit of out of order, but one thing you need to know, like when we said n is equal to a certain quantum number, L is equal to something, m sub L, all three of those give you what orbital you're in. But the electron identification needs m sub s. Basically, it's either a plus or a minus 1/2. The only way that you could separate a bunch of, let's say, hydrogen atoms, half of which have a spin up and half of which have a spin down, is to put them in this magnet, an inhomogeneous magnet. Half of them get attracted, half of them get repelled, and you see there's only two possibilities. That's the fourth quantum number. So 3 quantum numbers give orbitals, and 4 quantum numbers for electrons. This is just what I just said. There's 2 pathways in that experiment, either plus 1/2 or minus 1/2. So these are the 4 quantum numbers for electrons in atoms. It's like an address. Every single electron in an atom has 4 different quantum numbers. Okay? And so this is almost like an address. So even though you might have 100 electrons in an atom, every single one of them has like a 4-number code that gives you information about what shell it's in, what's the shape of the orbital it's in, which way it's pointing, and then which way the spin of that electron is, either up or down. So this is a summary. Each electron in an atom is described completely by a set of 4 quantum numbers. The first 3 quantum numbers describe the orbital. The 4th quantum number is the spin. That rule that I said no 2 electrons can have the same 4 quantum numbers, that's called the Pauli exclusion principle. An atomic orbital can hold a maximum of 2 electrons, and they must have opposing spins. I remember the other day you were telling me about electron configuration, where let's say you had the electron configuration of, let's say, calcium. Calcium has the argon core and then 2 4s electrons. And then it said, what's the quantum numbers of these guys? Well, n is equal to 4, and L, is equal to 0 because it's an s orbital, and then L is automatically equal to 0, and then m sub s is either plus 1/2 for the up electron or minus 1/2 for the down electron. So you could see that they have different quantum numbers. Well, that's it for right now. I'll maybe make you another one later from the next chapter. I hope this is helpful. Bye.